Welcome to It's a Controls Problem, where we do precision guesswork based upon unreliable data given to us by those of questionable knowledge. I'm your host, Charles Johnson. All right. Welcome, everyone, to another episode of It's a Controls Problem. I'm your host, Charles Johnson. I'm here with always, my great friend and podcast producer extraordinaire, Matthew Vanberg. Matthew, how are you?
I'm doing well, thanks.
And today we have been graced with the presence of a gentleman here named Gulai Shen. And Gulai is a research extraordinaire. And Gulai, welcome to the show. And why don't you go ahead and just give a little bit of background about you?
Oh, thank you for having me, Charles and Matthew. My name is Gulai. Currently, I'm a doctoral student at Harvard. I work at and do research at Harvard Center for Green Building and Cities. And prior to starting this doctor thing, I was working at a company called Nantum AI in New York City. I was a research scientist and later the lead of AI research at the company, the research and development team. And yeah, I started to get into buildings and energy during my master when I was doing my master's thesis, and also had the opportunity to meet the founder of our company, and started to do research both really in academia and in industry in the field. So yeah, and that's what brought me here today.
Well, great. No, absolutely welcome. Welcome to the podcast. But I'd like you to. So I know that you just gave a little bit of background there. But what really sparked your interest, in that intersection of architecture, engineering, and data science?
Right. So my background was mainly in mechanical engineering. At the time, I was looking around. Mechanical engineers can solve all the problems in the world. Yeah. So I was looking around to see what would be my field and what would be interesting problems for me to solve. And really, it started when the founder of Nantum AI, John Gilbert, who was a great guy who came and visited our lab at Cornell at that time, and gave an introduction about all the things that's happening really in the commercial office buildings, largely those high-rise buildings they have, with the system and what they are doing with the building, with the data they have from the building, and with the system, the operating system, they call it, for the building they have to what are they doing with it, and what they envision to take, smart buildings really to the next level. And that's really my first exposure to this thing. That's the first time I really understood there's this kind of field in both, it's actually pretty large, both in academia and in industry. So there are research groups, there's national lab, there's companies and government interests in this kind of energy sustainability field, and specifically in buildings, which is one of the, as you guys must have all known, one of the greatest energy user, carbon emitter, and all sorts of things. And so then really I just dived into it and continued for until now.
That's I think that's really awesome. It's any kind of automation, I think, can be quite interesting to understand. And once you break it down, you realize that there are so many facets to it. And you mentioned that your research at Harvard, and that seems really pivotal for this. So, what are some key projects that you've been involved with that have shaped your perspective on AI in buildings?
Yeah, I think it also really starts from visiting, the engine room of the building and see all the equipment and the BMS system that's running in the building. So I think one of the first project I was really get me into this field was working on optimizing the condenser water loop of the HVAC system, and yeah, so it starts really always um, researching what has been done by people, so how the BMS programs are done right now, and what is missing and what needs. Why do we need all these additional data and machine learning models and AI tools to help make it better? So that's like one of the first thing I started with, really just to help me understand all the equipments in the building, how they work, how they synchronize together, connected to run building at least robustly and safely over all these decades, and get some understanding of what's missing and what can be done more with all the new data analytic, data science, AI techniques. So the first thing I think we did was start to really testing and control some of the part of the equipment. So condenser water loop is one example. Like the first thing I really did. So I remember, of course, the most we were testing out how to set the condenser water temperature, how to set the cooling tower stagings, and everything really, and to bring in the large amount of data we have and test it. And the output, I think it was showing we actually published it recently at the ASME conference that it ends up being a human in the loop control. In the end, what we hand out to the building engineers was a operational table that a lookup table sort of thing, but it is updated on a monthly basis. When the model updates, we reproduce a new operation table for the building, for the engineers to follow. So we constantly catch, these changes in the environment, tear and wear in the equipment, and all these changes, and constantly updating it. And so yeah, that's I think one of the first thing. I think another major project I was very honored to be part of when I was working at Anthem AI was a project that a multi party kind of collaboration between national lab, between the USGSA and Anthem AI, where we were piloting out some of the algorithms we had in the GSA portfolio. So we started with a few buildings, implemented our machine learning driven control system, and that specifically was for, I think, optimal startup and shutdown, as well as an airside optimization where we are optimizing the AHU operation, the static pressures, fan speed, etc. And yeah, so we ended up piloting in a couple buildings, came up with a report that's validated, supported by National Lab, both Unreal and Lawrence Berkeley National Lab, LBNL. And we proved for the GSA portfolio across all the US, over $28 million potential saving on an annual basis just by implementing these new algorithms on top of all the existing controls and stuff we had. So that is another significant project I was involved that really showed me actually the impact of the things that we can do just by optimizing efficiency. There's no retrofit like a lot of work regarding putting new equipment or retrofitting the building. really just from the operation standpoint, with all the data and model we had to optimize the operation to generate this much saving. So yeah, those are two. And maybe I'll give one more, third one. That's more, I think, more recent, but also when I was in industry, actually, I thought most of the project would be more impactful industry as I can try to think of one that's more recent in the research, but maybe that one first. It's also implementing the other side optimization that I was mentioning previously. So it was also one of the largest customer for Nantum, which is JP Morgan Chase. Similar story, we started piloting out these algorithms in a couple sites, even starting from a couple floor, a couple air handling units, and gradually we showed the potential, the actual saving that was surfaced from those testing flaws, testing issues, and slowly gaining confidence from the building side, really, from the engineers to be confident of working alongside this algorithm, to understand the algorithm behavior and why it's doing this, when it's time to maybe step in and when it's time to put it back on, and to gain the trust, really, to work together with engineers and eventually expand to first the whole building and gradually over the different building, the whole portfolio of JP Morgan Chase. So yeah, I think those are the three stories I can think of now.
So with the cooling tower one first, with the condenser water, a couple questions I have as a follow up there. So with the cooling towers that you were dealing with, did they have VFDs on them, or was it like a main and pony motor, or a combination of both? And what did you feel was the best course of action to control condenser water? Were you trying to take cooling tower approach into consideration, or what variables were there to do that? So that's the first question I have.
Yeah, I think from the optimization side, what we are mostly concerned is they have like for a large commercial building that had, I think, for the specific building we tested, had 8 or 10 cooling towers that's sitting there. And I think one of the major question they would having was the efficiency curve for those fans. And they have some optimal point that basically for the same amount of heat rejection, it would be the most efficient, and depends on a factor or a different range of factors, including the supply, the chillness or the supply temperature it is said to be, and of course the amount of heat rejection that is required, and of course all the evaporative behavior depending on the ambient weather, the humidity, and really the air mixture that's on the rooftop. So typically, like engineers would, I think, roll off a simple load-based staging. When they have certain tonnage of cooling load required, they would turn on a certain number of fans, or potentially based on also maybe a wet bulb, based off the wet bulb of the temperature. So, but of course there could be many times that it is a bit blurry, like maybe 2 would work, maybe 3 fan would also work. So with the data we have, really it's about understanding, okay, that specific, we've recorded this amount of data for that specific tower and for this specific fan, and what's the actual curve it looks like. and to have that monitoring and model constantly being monitored and updated, so we can always have a most accurate understanding of that specific cooling tower. So maybe tower 1 had a bit more wear compared to tower 8. So really, it's about utilizing these data to have a more accurate model and constantly monitoring, updating these models to produce an optimal recommendation. And I think one thing, it's in terms of the objective, of course, it's about energy, but at some time it's also, people would also consider really to rotating between these fans, really to help elongate their lifespans and different components, pumps, of course, the condenser with the pumps, of course, also in this whole consideration.
So the second question I have for that, and then I want to ask one question about the optimization for the air handlers, and then I'll move forward. Did you find that for the condenser water for the condenser water optimization, did you find that the system had to have additional sensors to give you a better evaluation in your algorithms to determine the best course of action?
Yes, and I think now most of the BMS systems have enough points, I think, but for some of the older buildings, sometimes he always had a couple sensor missing or a couple sensor, having problem. And at the same time, it's also about, so the whole onboarding or commissioning of a software, like this whole process is tricky. There's a lot of, I think, menu thing that we have to go in and see which sensor is which. And of course, different buildings, the different BMS system they have, and different BMS programmer who set up the building might have different, different naming conventions and different things. So we have to really find those points. And yeah, like sometimes we find all kinds of problem with it. And of course, another aspect is to have our algorithm running. We require, because to have an algorithm working from building to building, we require certain structure in the data. So when we gather data, it is also about how the data will be stored. Like, are they tagged correctly? Can the algorithm understand, like, this is which pump that's connecting to which loop? If there's a secondary loop, there's some other pump. So there's a lot of these things to really understand, I think, digitally what the building looks like. It's like almost a digital twin of the building, of the actual system. So yeah, there's these kind of things that we need. And the other part is, I think, sometimes we just don't have enough data yet. Like, I think in most BMS system, while some data are stored for some period of time, normally we come in, we see those things sometimes, especially for a new building that we just came in. There's not enough historical data. And maybe one of the equipment, one of the backup fan was never really used. So we cannot observe those data. And also, I think another interesting aspect would be when we see the data, because the building has been operating in a pretty consistent way to be safe and to be, based off the rules. A lot of scenarios would not be observed just from the data. So when doing optimization or when modeling, it means, especially data-driven models, it means we can only be as good as what we have observed from the data in a purely data-driven way. So in that case, as I mentioned, we could have data we don't have. We could have the scenarios that was never observed. And so all these are the potential challenges that it faces when you try to implement a machine learning or AI-based solution that on the foundation of it is largely really the data.
Okay. Um, with the air handler optimization, as most of our audience knows that you can we typically implement optimal start, so we take the building envelope calculation, outside air temperature, and determine a time when a unit should be able to start and get the building to a relatively comfortable position. But what a lot of people don't really use is the optimal stop. So, air handlers could theoretically coast, to, they could actually turn off earlier than expected to allow the temperature to still maintain comfortable just as to get us to the unoccupied time. So with that, did you see us with your research? Did you see a significant um, a significant difference of how early we could shut off units in order to coast into unoccupied times?
Yeah, definitely. So optimal start and stop. It's. I mean, optimal start, as you mentioned, has many people have tried to implement it, and optimal stop, on the other hand, it is a bit tricky. I think at least you don't want to. You have to consider really when people start to leave. You have to consider also the different weather conditions, and maybe it's also about really the thermal perception of the people when it's getting end of the day, and you're going to leave, and you might have 10 minutes, 15 minutes that temperature is drifting away, and it's almost like inviting you to leave. So there are different to things. So for a space that if we typically have in those commercial offices, I have experience with. First thing I think we have to convince is to relax your lease agreement, service level agreement a little, SLA a little bit. And so if you are required to have a hard stop for, 6 p.m. or some time for the exact temperature that you assigned for, then really I think would be helped with was really through the data to model that really the behavior you mentioned, like how much of the thermal inertia it would take you safely out of the range. But the other aspect I think is very important is what I said about the occupant perception, and really to model the occupant comfort, and that's I think what my current research kind of was trying to focus on is really to have to develop models that really to perceive and to predict, perceive, and really interact with how much the acceptability of thermal comfort at different times. So, and with that, and of course, we have with that, the first important thing is to understand the occupancy in each floor and zones. So if the floor is empty already by 3 p.m. and you're still running off based on your lease agreement schedule to 6 p.m. because you're wasting so much energy. So first of all, this time of comfort, that the limit to be flexible, and that is really a function of occupants. And when people leave or when people come back, or when the space will be empty. And so that's the first thing. And then with this time now being flexible, again, we incorporated what we previously incorporated is those thermal models that basically predicts the interior temperature that based off a function of the current temperature, the outside weather, solar radiation, and of course occupant. So with that, typically I think from shutdown savings we would able to achieve something around 1 to 2% with a pretty on the building level with a pretty strict constraint that we had. But I do think there's more potential for that specifically because sometimes we couldn't have floor by floor occupancy or even more accurately zone by zone occupancy. Sometimes floor is really limited by some some critical zones. And a building is sometimes really limited by a floor where you have to keep the central plants running a bit longer because of couple floors. So these requires, I think, definitely more data and more understanding of the occupancy and where are the occupants. And another big missing part that I mentioned is how to get these occupants occupant information. Like, how do you understand if they would be comfortable or not comfortable? So buildings, in large commercial buildings, at least from my experience, normally it's a very one-way report. Like you just give a hot call, cold call to the engineers of building, but the buildings are not really the engineers of the system of the building are not really understanding and predicting what would cause the comfort or what would cause the discomfort. So this also requires a bit even more modeling. Now we're talking about modeling individual occupant behavior, individual occupant preferences. And people have been starting doing this a lot in research and experimental settings. But ways to understand to largely implement to implement these things at scale is really a challenge, right? To understand the occupants and to have them have an intuitive, not intrusive way to interact with them, and to have the occupants be able to impact the control and to have the controls understand what it would impact the occupant. And that would really bring further the not the shutdown, the early shutdown of the building, of course, but also more intermediate and more granularly different time during the day. There could be more potentials to do some kind of modulating, like when people are leaving for lunch, most of the spaces would be empty for some extended period of time. When there's an event gathering and people are gathered at one floor, one zone versus spread it over different zones. So yeah, like these things, more data and more understanding of those would really help.
Great. No, I think thank you for those answers. I think that gives people a bit of perspective that it's not always a simple answer of this, that, and the other. There are a lot of considerations that you have to take on in order to come up with answers, and it's not necessarily a formula of just this is how it goes exactly. The data is continuously changing. And because the data is continuously changing, you have to continuously change too, which I think is great.
Yeah, definitely.
Yeah. So let's move on for a moment here. As you know, AI really is a broad term, and so could you take a little bit of time to break down the specific types of AI, like machine learning or deep learning, that are most relevant to building automation systems?
Yeah, of course. So I think AI now, when people hear AI, automatically. It's about large language model. It's about ChatGPT, and that has been AI has been around for many decades. So it's longer maybe than. So the term has appeared very early in, I think, in the 60s, 70s, and right, and I think my professor, who's at my dad's age, at that time, the earliest form of AI, what IBM and those companies were developing was sort of the expert systems that people at that time sort of AI as logical thing that we basically transplant the whole human logic, how we approach things and how we logically think about things and have them program into the computer, and then they can solve all sorts of things. So, of course, that didn't work out well. Then we hit the AI winter, and really when AI started to take to take off again was really the booming of the data and the whole shift of paradigm. When people think about AI now, it's more about the statistics and about learning, the probabilities, the distributions, and largely in a Bayesian way of thinking about probability of things, and that's really changed. So I think if we're going a bit forward, before ChatGPT, people were thinking AI. If you remember, like the AlphaGo, like or things that can play Atari games that's really well. That's based off reinforcement learning rather than large language models. Reinforcement learning, which is more like learning through trial and error, and it worked perfectly for playing games and in simulations, mostly because you don't have a penalty of failing, really much a sort of like a risk or a realistic risk of breaking things in real life and causing, losses or even casualties or whatever. So at that time, that was a bit before, and even a bit more before, when people talk about AI, they were thinking about, I think maybe like image processing, computer vision sort of things, or similar time, maybe robotics, autonomous driving, when people are dealing with image data. So using LiDAR, we got using radar, LiDAR, you got like point maps of the environment. And those were largely based on supervised and unsupervised learning, meaning you're trying to recognize some object, or you're trying to adaptively get some understanding of the environment, of what this image does, and what should be the next action of my steering, of my brake and gas, and more before that, I think it was becoming something even simpler tasks, like the mails in the post system. They're trying to recognize the digits, recognize the postcode, zip codes, sorry, and recognize the handwritings and doing all these kind of things. So yeah, so AI is really the exact technology or algorithm that are being widely reckoned to represent AI of that time has been changing. So, and now coming to buildings. Buildings is really interesting thing that if you consider really the whole building environment, it is really a system that consists of or made up with all kinds of system underneath. So mostly, I think we are talking about control of the HVAC, control these mechanical system in the buildings, but also buildings have lighting systems, elevator, the internet, the fire, and the domestic waters, and really everything, because like it consists of so many things, and there are so many purposes for buildings, right? It's for humans, of course. Sometimes it's industry facility, and there's certain type of processing that's happening in the building. There's certain type of maybe it's a certain type of manufacturing or certain type of activity that taking part inside a building environment. So from the most common types of buildings at commercial offices, it's, I think, a large residential, the multifamily residential buildings, these kind of building that has a central system, like a BMS, a BAS system, that's managed professionally by a group of engineers. So I think those are the first ones to experience sometimes most of these new technologies, like when, for example, from computer vision. So now there's cameras in the building that can count number of people. There are different technologies, even just simply for counting number of people. They're using these computer vision. They're using all kinds of modeling that's inferring occupancy using CO2 sensors, using noise sensors, using vibration sensors, or even using thermal images. So all these things that you have some sort of input, and you're outputting a prediction of occupancy, number of people, or even where the people are, or identity of the people. There's typically some supervised model that's a supervised learning model that's powering these. So you have a lot of training data to you train on a lot of images you have seen with labels, and then you deploy those models in the field to really understand, okay, now I can detect an occupant that's walking in, and I can detect from the thermal image, I can box this region as human activity. I can detect what is the type of the activity or movements, right? And so these are, I think, one of the first uses. And then for building operations, now it's touching, we get all these data even without doing control. We can start to understand the buildings, right? There's all sorts of reporting that's happening around the building, how much energy consumption, and how can I predict how much energy I'm going to use when making my energy purchase for next year. Like how can I know how much I should block for my energy use, and maybe how can I predict and distribute those energy bills to each of the unit for multifamily residential buildings without installing 100 water meters to each unit. How can I or energy meters to each unit? How can I distribute from the disaggregation of these meters too? And that is also powered by all the machine learning models. And also now we get to, I think, the control part, which we mentioned, the reinforcement learning, and also other sorts of model-based optimizations. So, of course, that works for playing Go and other games, but people are already testing it to see if it would work in buildings. And as I mentioned, it is a trial and error approach. So it is dangerous and risky to implement in real buildings. So what happened is people building simulators for the building, that's the digital twin of the building, another also, to really have a control agent to start just like playing games, to playing the simulator. What is the best way for me to operate the buildings? So they train these kind of control agents, and with some guardrails and safety backup plans, fallback plans, to slowly put it into real action in real buildings. So yeah, so that's also another example. More recent one would be, for example, the language model. How could it help in buildings? Of course, there's many ways buildings can utilize these use GPT or cloud or these kind of models that to help, for example, generating for the operators of the building and managers of the building to help basically scan through all the documents and bills and generating reports, generate understanding what's your energy consumption, and to basically ask questions to your buildings that has huge amount of data, huge amount of documentation, to scan through your BMS document to understand what's happening. And some of the most latest things people start to do, interestingly, with one is with a fault detection diagnosis. When you see with all the data now you have for the building, when you see some anomaly happening, you would want to know what caused it, and it sometimes typically takes a very experienced engineer to scan through data and go through equipment, so checklists, so things to understand, oh, this could be the reason. But now with the reasoning capability of these models, they can see the anomaly, understand from its word knowledge, in addition to all the documentation it might get access to for specifically for the building, to reason and analyze what could cause it and go checks data. Is it really supporting this, and come up with some diagnosis of what could be wrong and some plans that how you should maybe resolve this fault or resolve this abnormal scenarios. And those are the examples I think mostly for commercial residential building. We have Occupy, and for other building that, for example, that I'll just give another example for like an industry type of building where you might have poisonous gas that you need to be treated carefully, when it might be dangerous for humans to actually get in and see. And through the use of sensors and detect certain type of gas, you can understand the distribution of the gas inside the air or even outside the building, and build a model that understands the dispersion of these air particles and trace back to see where could the leak of those poisonous gas coming from, and really pinpoint, maybe it's a pipe breakage or some unsecure connections that causing these kind of leak. And those are also powered by these models and these algorithms that we can now or generally call AI. So yeah, I think there's much more, tons of other examples that people could come up with, and working on different fields. And the interesting thing is it happens to us, all these people would probably happen to be in a building somewhere, and for their specific task, and yeah, so it's really everything.
I guess the question I want to ask now is one thing that you definitely have touched on is that when it comes to data, and for a building to have to give you a really good model into understanding the proper optimization. Clearly, there are times where buildings are lacking, whether it's the number of sensors that are being used, or one, as you pointed out, where like you had a bunch of fans that were backups, and those backups aren't really used, so that you couldn't really take data from them and put that into your calculation. So, having said that, what kind of investment do you think, from a legacy perspective, maybe potentially in terms of dollar amount, you think would have to be, invested in order for AI to really kind of, spin its wheels and give you a good, estimated guess on better optimization?
Yeah, I think the responsibility and of both the party that's the building owners or operators, but also um, algorithm providers or software providers. And really, if I'm even though I'm being on the software or algorithm side of the things, I really hope that they would have to pay building owners, or they would have to pay $0 to spin up these things, these code. You could have a magic box like an iPhone that you get delivered in one box, and boom, you're running, you are connected, and your equipment start to run. And but unfortunately, it's not there yet. We at least to have the algorithm being able to control the building, the data has to be just from like in real time control point of view. The data has to be streaming from the equipments to the algorithm, either through cloud or on the edge locally, with some computing device. But and at the same time, there has to be the control signal has to be able to send back and really act on the equipment. And so those part of things were still largely dependent on the existing control system, like all the BMS BAS systems that takes in which are great at taking schedules or set points and just do set point tracking and steadily and robustly control these equipments. So there's this connection that has to be put on. That means money, and sometimes it might be it just be the hardware, but also the cloud infrastructure maybe it runs on that requires maybe cloud computing and sorts of things. Or if it does not have anything on the edge that's test computing power. And of course, the things you mentioned, the other part of the cost is like how much time you really needs to gather these data, to have the equipment sit there and just feeding data in until something really useful can start to take impact. And I think that that is more solvable from the software standpoint. So you have a new equipment that you don't really see it how it runs. You have some maybe manufacturer curves, and maybe you have some similar equipment that's sitting around or in other buildings. So that is a relatively easy problem to solve. That from you can have better algorithm that requires less and less data. I think initially, from my experience, what we developed for optimal startup, for example, initially we were requiring a couple years at least of data just to understand, the different seasonal behaviors, right? Different across different temperature, to have data available in the extreme winter and versus in the summer. And gradually, as we get more and more connected to more and more buildings in different zones, these really can be solved through either transfer learnings or with some sort of physics aware or physics infused model that we are doing things. We have all these great simulation, physics-based simulation tools that's developed for decades, like Energy Plus and things that can do a reasonable job, like to give a reasonable estimate, a good a baseline for what we expect certain equipment or certain the thermal behavior of the building of the space, and really to combine it with maybe the limited amount of data we would have accumulated from the specific building, and with a large pool of buildings and equipments that people would we had access to really transfer the knowledge from another equipment to this equipment, another building to this building. And that's what really speed up the whole process from requiring a couple years of data to I think in the end we achieve 2 weeks. So we just need a 2 week of calibration for the whole building, and we see infrastructure. You can start to see savings, and that saving would be adaptively getting better and better as we get more and more accurate understanding of the specific traits of this building, of this equipment. And for some smaller part, so some other like the airside optimization thing we previously mentioned, it requires no historical data. We started right away, and that is through and it learns through the interactions from it. So we have we know how to model the airflow and fan pretty accurately at the small scale, and we start off with the best. We grab the model number, the horsepower of the fan, everything, and we have a very much reasonable model to start and to give you savings. And it's really what's required now is still just the flow of the data, the flow of the control signals, and these infrastructures. And yeah, I think depends on the specific application you would want to have. Like if you would want to understand occupancy at zone level, then of course you still need more sensors, and it's really a combined effort from both sides. Like have to put initial investment into the building to have these knowledges, and from the algorithm and the developers of these AI software side, the effort is really trying to really minimize such a cost. And that's why I think this industry is so it's interestingly both thriving in academia and in industry. So both sides are working towards this goal. And I said, like, hopefully there will be a magic box that you plug into your building and boom, everything would work. But that's I think that's the direction it's going.
That's a very good answer. You absolutely have a lot of insight in AI for sure, and I really have appreciated everything that you've brought so far to the table to educate our audience. But I do want to talk about your research on people hour, and I think it's actually really fascinating. So, can you explain that concept and how it provides a more occupant-centric view of
Absolutely. The people hour. So it's a cool name. I think I have to admit first. We came up with this and we liked it very much. But it's a simple idea actually, that basically you understand your occupancy at any time, but also the duration of occupancy, and to represent those together. Basically, you understand 1 people hour will represent one occupancy for 1 hour. And that really gives you a better understanding of the space use, specifically for buildings that's designed to, like for office spaces, it's designed for, for office workers to really utilize the space. And we identified the reason why we would want something to like this is when we evaluate the energy performance of a building traditionally, and it has been the EUI, the energy use intensity for the building, right? That's simply you have your energy and you just divide it by the the floor area you have, and you have some variation. Different standard depends on the type of the use of the space. And so COVID hit a few years back when people began to vacant, when buildings were being a bit more vacant, right, during that time. And what we firstly observed was, even though we had maybe 1%, 5% of normal occupancy, and the energy use compared to when we have fully occupancy for those buildings was still 80%, 90% of what it normally consumes. So basically, over 90% reduction in occupancy resulted in 10% reduction in energy, which is not ideal. And basically, all these energies are used to power an empty building. And that's why we begin to see if there's a better way to illustrate this more clearly to people, and to show that when you evaluate the energy efficiency of a building, it's really about, of course, energy is your input, but how do we represent the output so we understand the efficiency better? And for an office building, it's about the occupancy, right? The productivity it would have, and the most direct representation would be how many people you are hosting and how long you are hosting them for. If you are providing a comfortable and healthy environment for 100 people, of course, you should technically, if you guys have if the two building has the same efficiency, you would use more energy than another building that's hosting 50 people hour. So that's why we started to, we have the luxury to have the mid-level occupancy data for the building. And we started to do this simple calculation from pre-COVID time to post-COVID time to basically trace what the building was behaving and what's the COVID impact and how the recovery is taking shape. So we found, interestingly, in a portfolio that's mainly office buildings in New York, and a super efficient building that's pre-COVID turns out to be one of the least efficient one if we adjust it by people hour. So turns out that building had just had a major tenant move out. So it being empty, and it's going to have a major retrofit taken place, and it's and also, I think, delayed by COVID. So the building was empty, and it using, on paper, normalized by the square feet of the building, least amount of energy, or not least, one of the least amount of energy, but it's hosting, I think, zero occupancy, zero tenants. And so the people hour, when you normalize it by that, it turns out you are just dumping this energy to empty spaces, versus another building that has the highest occupancy rate, has the most people staying for the longest period of time, and to getting a not good grade from Energy Star. And when we do this, it's actually one of the most efficient building in the portfolio, and comparing to other similar buildings. So that's what we are trying to highlight there. And Yeah, it's really to push a better way to maybe understand performance of buildings specifically for and maybe commercial offices or other similar buildings that's maybe commercial spaces also. That's really a function of how much people you're serving versus a traditional way of simply normalizing it just by how large the space are, but really how well they're being utilized.
So we hear a lot about AI and decarbonization. And so, how can AI be a critical tool in helping buildings achieve net zero or even potentially positive energy goals?
Right. Um, to of course, so buildings have to be more efficient, as you said. You have to. I think for US specifically, we are already or we peaked on the energy consumption and carbon emission nationwide. We are on the path to be net zero, and that requires building which is 30-40% of the energy consumption and 70-80% of electricity generated that's used by building. So it's really a big task for to remove all these carbon that's being all these energies and all these carbon that now that's being attributed to the building sectors. And there are ways that you can there's one way to answer this question is we don't need to be even more efficient, just electrify all once we are all electrified and just make the supply side 100% renewable, and boom, you have no carbon penalty now being seen on the buildings from a demand side point of view. And that is logically that is one way to think about it. But to from the demand side, the other problem is, okay, now I have these a carbon reduce. That goal would be, let's say, presumably that's hypothetically met, but I'm still consuming same amount of energy, and then the problem become really a cost-wise problem. So energy prices would increase to help fund all these new renewable to build all these renewable plants, and it will be extremely expensive, especially for US, like the for the Northeast offshore wind plant is already costing much more than what it planned. And I think people also start to seeing the energy price increase, not only in West Coast or Texas, but also now more recently, I think from the East Coast, now we have more and more expensive electricity price and so on. So from a building owner point of view, you still need to be more efficient, reduce, essentially now come back to the cost. So that's the motivation. And then how to really achieve that? How can we be more efficient? There's really only so much can do from a rule-based system that you run off simple rules, and you have a simple objective of course, say, for example, minimize the energy at any given time. But there's also the need for comfortable and healthy indoor environment. Now, since COVID, the ventilation requirements now gets more and more attention. How much fresh air you should bring in, and under those constraints and or a new objective to have enough ventilation, you're adding in another objective to operation. And even with a grid with a significant portion of the grid to be renewable, you still get problems like the transient behavior of the renewable, like solar. Of course, you won't get it in the evening. For wind on the East Coast, it's more prevailing in the evening versus. So now you have to consider time of use for energy when you try to be more efficient, but also when you try to be more carbon neutral, carbon negative even. Now another objective comes in, and then you have all the constraints also from the grid for considering, stability of the grid and the transmission constraints. And yeah, so buildings are now, if you really want to be efficient, you have to consider, to meet your carbon and energy and cost goals, you have to consider all these aspects and see as I'm talking through this, I'm already lost. Like, what would this like million different things maybe to have to be coordinated and to make an optimal decision that would not be trivial, even for a simple action for a building, let's say, had a battery system installed. It would not be a simple action to say when to charge, when to discharge, and at what rate. So these problems becomes out of you cannot find a trivial solution that satisfies all these and be efficient, be optimal. That's require a system that's specifically, deliberately, carefully designed to tackle these problems and under these meticulously designed objectives, and understanding the constraints in real time. And you have to have the capability to predict certain future things, like whether, like the availability of renewable energies, like when will your occupancy arrive, and all these things. So it becomes so complicated, and it requires an AI system to coordinate. And the complexity also in that case becomes it becomes a scale problem. So we have the whole building stock and potentially the grid and all the EVs that would be connected and have an interplay on how much, what would be the carbon intensity in real time for the electricity, what would be the energy demand and the consumption, and what will be the price, the cost of energy in real time. So all these become interdependent, and you have to have understanding or coordination across from building to building, from one campus to another region, neighborhood, from even from a building to a nearby power plant, solar panel, or nearby EV that's connected to the grid. So again, this becomes a non-trivial problem that requires a specifically designed system that have the ability to talk to each other, understand, to have a objective, a coordination, and to have the, if not most optimal, some level of optimal solution that would really help to solve this whole problem.
So, there's a question I have here. You know, when it comes to collecting all this data that we have, obviously there's a concern for privacy. So when it comes to ethical, or I guess the question I have is, what kind of ethical considerations comes into play when you're using AI and like IoT to collect this data on a building's occupants? Like, how do you balance innovation?
Yeah, that's another great question that people are considering, and that's really a lot of consideration about privacy and data collection that requires this that is maybe preventing some of the algorithm to be implemented in real world. Like, for example, a simple way to understand occupancy, what we tested on is to just have access to all the Wi-Fi access points, the data. So we know like all the electronic device will be picked up by the access point, even though you're not going to be connected to the specific Wi-Fi, even if it's just a public Wi-Fi. Your MAC address would appear on those access points, and through some algorithm, it is possible to understand if it's occupied, and with no limitation. I at least we didn't try, but maybe there's something more personal that could be understood and extracted from these kind of data. And are they good? Yeah, like if we could have just utilize the existing infrastructure of these Wi-Fi networks to understand floor by floor, zone by zone occupancy, that would generate great potential. That would have great potential for energy savings and zone by zone control and occupant-centric controls. But would this be allowed in most of the buildings? And that is not. That's why this thing was not capable of being implemented now in the wild, and so there's these constraints. So what would be the solution around that? Of course, I don't have a perfect answer. There's always a balance. There should be guardrails, guidelines around how the data should be used. So for example, when we develop the algorithm, you can strictly have it to be identity free. So there's no identification of each person. Like there's just, it just understood as a occupant, or, a noun. It's not identified to be anybody or used for any else. So the algorithm would not do anything. And maybe the level of data will be accessed can be masked or hidden with identity to just be strictly codes that would not have any identity issues, identity informations, or anything. So even you have the access of the data, it will be general. There will be no personal information or anything. Another aspect may be the use of image. So again, these are largely, if you have direct image data, you can identify number of occupants. You can even identify what clothes are they wearing. So it depends. It can have varying comfort perceptions. You can identify the actions they're taking. So if they're sitting there versus if you're playing ping pong in the office, of course they would have different thermal sensations. So how you can modulate these and improve comfort and save energy. But again, so use of these data would subject to the right of use, or kind of would people be comfortable giving access to these data? But on the technology side, people are developing ways to be more privacy preserved. Like instead of using a camera that's taking RGB pixel information, like to reconstruct a full image, it becomes a thermal image that now it becomes it can hide the identity of a specific individual, but still understand the occupancy of the people, and it can still understand actions and certain things. So again, this should be an effort from multiple parties. it's in some experimental settings. Of course, it's more relaxed in research. It's just proof of concept and trying to find ways that better that use probably least intrusive, uses least amount of information to make the same thing happen. And on the other side, there's really the how how to use this data and who's allowed to use what's the visibility at different level. And lastly, I think it's also important to gain the occupant trust, the people's trust. Like, how can you understand more what is going on to make you feel more comfortable of you're knowing what you're sharing, you're knowing what can be taken to the algorithm and what cannot. And just like on your phone, you can turn off certain things to preserve privacy, and that might impact performance of certain software by a little bit, but that's a trade-off that you can make. So these are all that's from my experience. I'm not really an expert on these. People specifically study and research on privacy, fairness, these kind of things in AI systems. But at least for buildings, that's more the practical side of it.
If you could give one piece of advice to a student interested in a career in sustainable and intelligent buildings, what would that be?
That question might take some time. Normally, I'm the guy asking for advice. But if I really have to give advice, is I think if you want to get into this field, of course, it's a huge field. As I said, you can see from national level, what level there's these goals of sustainability, carbon goals, energy, and cost, and for the people, this is the one of the hottest field right now, and it's a field that's evolving. Like from time to I can see from my interaction with much more senior members who worked in the field. I can see them how the latest technology has been shaping, has changed the industry, has changed the field, and getting into this great time when we have the boom of the data, machine learning, AI, and to implement on this field, I just found it exciting. And if you're a student and when you walk on the street, you are the type of guy who would look up a building and you see a certain floor block out and you were interested. Why doesn't that floor have the normal facade? Because it's an engine room, and if you're interested in these kind of things, then yeah, just read about it and see if you really want to get into it. That's it. I don't have much more. Yeah.
One last question. I just thought about it. So, since you've been so immersed in this research, and originally you you originally were going for mechanical engineering. Let's say you went back to be a mechanical engineer and working for a firm. How much of what you know now when it comes to optimization and such, how does that look when you were, if you were to create a plan for, like let's say a building automation system?
I think mechanical engineering, again, recalling from my undergrad time, it's really a field that we are learning about structures, we're learning about statics, dynamics, we're learning about materials, we're learning about heat transfer fluid, and you find all these things in building, right? If you find the structure of the building, you find the thermal insulation, how you're gonna insulate the building, different. You find the airflow, how it's gonna impact the distribution, and with that experience, I think it's really adding on to top of all the data science and machine learning AI type of thing. You become you have the advantage of the expert knowledge in the specific field. You have the domain knowledge, and now you're gonna on top of that, adding all these new things that you see can be implemented to the problem. You understand the problem better. So if I were to go back, like to come back, and that's really, I think the more important thing of course, is to identify the problem, and all these engineers experienced, and we know they understand very well, like what each equipment does, what's the limitation, what's wrong, like each of the little things. And with a clearly identified problem, it's really just implementing these new tools to customize it and for the problem. So it becomes powerful when you combine those two things, and that really solves a realistic problem. I don't know if I drifted away a little bit from your original question, but it's really, I think, the foundations I'm mentioning, which is what all these BMS or all these traditionally, or you can call it traditionally, building or architecture firms are really good at, who operates the building, design the building, and to have the privilege to also be on the more data-driven data science or the machine learning side of it. It's really boosting the capability to solve the specific problem.
So, Gulai, I really just do want to thank you for taking the time and sharing your knowledge. And clearly, it is evidence that you have done all the research.
Thank you so much, Charles. Thank you so much, Matthew.
I appreciate it.
And yes, great. I love to be back. It's nice chatting with you.
Great stuff, Gulai. Thank you.
All right, well, that's all we have for this episode. And remember to stay curious, and the devil is in the details. Until next time, I'm Charles.
And I'm Matthew.
And this has been It's a Controls Problem.
There's not too much work for Matthew to do.